Growth of functions. The order of growth of the running time of an algorithm is defined in Chapter 2, gives a simple characterization of the algorithm's efficiency and also allows us to compare the relative performance of alternative algorithms. Once the input size n becomes large enough, merge sort, which is with its theta of n log and worst case running time beats insertion sort, whose worst case running time is theta of n square. Although we can sometimes determine the exact running time of an algorithm as we did for insertion sort, the extra precision is not usually worth the effort of computing it. For large enough inputs, the multiplicative constants and the lower order terms of an exact running time are dominated by the effects of the input size itself. When we look at input sizes large enough to make only the order of growth of running time relevant, we are studying the asymptotic efficiency of algorithms. That is, we are concerned with how the running time of an algorithm increases with the size of input in the limit as the size of the input increases without bound. How the running time of an algorithm increases with the size of the input in the limit. And the limit is a mathematical thing. Limit n tends to infinity, for example. Usually an algorithm that is asymptotically more efficient will be the best choice for all but very small inputs. This chapter gives several standard methods for simplifying the asymptotic analysis of algorithms. The next section begins by defining several types of asymptotic notation, of which we have already seen an example in theta notation. Theta notation is one of the asymptotic notations. We then present several notational conventions used throughout this book, and finally we review the behavior of functions that commonly arise in the analysis of algorithms. Asymptotic notation. The notations we use to describe the asymptotic running time of an algorithm are defined in terms of functions whose domains are the set of natural numbers. Such notations are convenient for describing the worst case running time function, which usually is defined only on integer input sizes. We somewhat find it convenient, however, to abuse the asymptotic notation in a variety of ways. For example, we might extend the notation to the domain of real numbers or alternatively restrict it to a subset of natural numbers. We should make sure, however, to understand the precise meaning of the notation so that when we abuse, we do not misuse it. This section defines the basic asymptotic notations and also introduces some common abuses. Asymptotic notation, functions, and running times. We will use asymptotic notation primarily to describe the running times of an algorithms, as when we wrote that insertion sort's worst case running time is theta of n square. Asymptotic notation actually applies to functions. However, recall that when we characterized insertion sort's worst case running time as the n square plus bn plus c for some constants a, b, c, by writing that insertion sort's running time as theta of n square, we abstracted away some details of this function. Because asymptotic notation applies to functions, what were writing as theta of n square was the function the an square plus bn plus e, which in that case happened to characterize the worst case running time of insertion sort. In this book, the functions to which we apply asymptotic notation will usually characterize the running times of algorithms, but asymptotic notation can apply to functions that characterize some other aspect of algorithms, the amount of space they use, for example, or even to functions that have nothing whatsoever to do with algorithms. Even when we use asymptotic notation to apply to the running time of an algorithm, we need to understand which running time we mean. Sometimes we are interested in the worst case running time. How often, however, we wish to characterize the running time, no matter what the input. In the other words, we often wish to make a blanket statement that covers all inputs, not just the worst case. We shall see asymptotic notations that are well suited to characterizing running times, no matter what the input. Data notation. In chapter 2, we found that the worst case running time of an insertion sort is t of n equal to theta n square. Let us define what this notation means. For a given function g of n, we denote theta of g of n, the set of functions, as f of n such that there exists positive constants c1, c2, and n naught such that 0 less than or equal to c1 g of n less than or equal to f of n less than or equal to c2 g of n for all n greater than n naught. Within set notation, a colon means such that, okay, what they're referring to is this thing, this part. What they are trying to tell is, a function f of n belongs to the set theta of g of n if there exists positive constants such that it can be sandwiched between c1 of g of n and c2 of g of n for sufficiently large n. Because theta of g of n is a set, we could write f of n belongs to the set theta of g of n to indicate that f of n is a member of g of n. This is belonging sign. Instead, we will usually write f of n equal to theta of g of n to express the same notion. You might be confused because we abuse equality in this way, but we shall see later in this section that doing so has its advantages. Graphic examples. The graphic examples of the theta, omega, O, and omega notations. In each part, the value of n naught shown is the minimum possible value. Any greater value would work. So theta notation bounds a function to within constant factors. When we write f of n equal to theta of g of n, if there exists positive constants such that at and to the right of n naught, the value of f of n always lies between c1 of g of n and c2 of g of n inclusive. O notation gives the upper bound for a function to within a constant factor. So omega is like the lower bound, O is like the upper bound, and theta consists of upper and lower bounds. Got it. That is one thing. The other thing is, what does this mean? What does this bounding mean? A function f of n belongs to, we read it. Figure 3.18 gives an intuitive picture of functions f of n and g of n, where f of n equal to theta of g of n for all values of n at. So what we want to see here is insertion sort. This is g of n. This is f of n. Intuitive picture of functions f of n and g of n, where f of n equal to theta of g of n for all values of n at n to the right of n, or the value of f of n lies at or above c1 of g of n. Okay, in other words, for all n greater than n naught, the function is equal to within a constant factor. Tight bound for f of n. The definition of theta of g of n requires that every member f of n belonging to theta of g of n be asymptotically non-negative, that is, f of n be non-negative whenever n is sufficiently large. An asymptotically positive function is one that is positive for all sufficiently large, and consequently the function g of n itself must be asymptotically non-negative, or else this set theta of g of n is empty. We shall therefore assume that every function used within theta notation is asymptotically non-negative. This assumption holds for the other asymptotic notations defined in this chapter as well. In chapter 2, we introduced an informal notion of theta notation that amounted to throwing away lower order terms and ignoring the leading coefficient of the highest order term. Let us briefly justify this intuition by using the formal definition to show that half n square minus 3n equal to theta of n square. To do so, okay, this function, this f of n, belongs to the set of theta of n square if there exists some value c1 of n square and c2 of n square such that this function can be bound in between those two functions. What this means for me is that when they're trying to simplify this function, this half n square minus 3n, they're trying to prove that it doesn't come below a certain point, it doesn't go above a certain point, it is tightly bound to the functions of n square. So we can call it more or less as n square. To do so, we must determine positive constants c1, c2, and n0 such that for all n greater than n0 dividing by n square yields. Okay, we can make the right hand equality hold for any value of n greater than or equal to 1 by choosing any constant c2 greater than or equal to half. Likewise, we can make the left hand inequality hold for any, thus by choosing c1 equal to 1 by 14, c2 equal to 1 by half, and n0 equal to 7, we can verify that 1 by n 1 half n square minus 3n belongs to theta of n square. Certain the other choices for the constants exist, but the important thing is that some choice exists. Note that these constants depend on the function half n square minus 3, and a different function belonging to 3 theta of n would usually require different constants. We can also use the formal definition to verify that 6n cube is not a it does not belong to theta of n square. Suppose for the purpose of contradiction that c2 and n0 exist such that 6n cube less than or equal to c2 n square for all n greater than n0, but then dividing by n square yields n less than or equal to c2 by 6, which cannot possibly hold for arbitrarily large n since c2 is constant. Intuitively, the lower order terms of an asymptotically positive function can be ignored in determining asymptotically tight bounds because they are insignificant for large n. When n is large, even a tiny fraction of the highest order term suffices to dominate the lower order terms, thus setting c1 to a value that is slightly smaller than the coefficient of the highest order term and setting c2 to a value that is slightly larger permits the inequalities in the definition of theta notation to be satisfied. Okay, the coefficient of the highest order term can likewise be ignored since it only changes c1 and c2 by a constant factor equal to the coefficient. As an example, consider any quadratic function f of n equal to n square plus bn plus c, where a, b, c are constants and a is greater than 0. Throwing away the lower order terms, ignoring the constant yields f of n equal to theta of n square. Formally, to show the same thing, we take the constant c1 equal to a by 4, c2 equal to 7a by 4, and n naught equal to 2. Max of b, that is this makes it negative to positive. We just take the value max of p by, we are ignoring the sign basically, max of p by a and root of c by a. You may verify that 0 is less than or equal to c1 of n square less than an square plus bm plus c less than c2 of n square for all n greater than n naught. In general, for any polynomial p of n equal to summation of I to 0 to d, what is t, where the constant, where the a of I are constants and a of t is greater than 0, we have p of n. Okay, what they are trying to say is that for example, if we have a quadratic equation, it belongs to theta of n square. If we have a cubic equation, it belongs to theta of n cube. If we have a equation with n to the power 4, we have it belongs to the theta of n to the power 4. Since any constant is a degree 0 polynomial, we can express any constant function as theta of n to the power 0 or theta of 1. This latter notation is a minor abuse, however, because the expression does not indicate what variable is tending to infinity. With We shall often use the notation theta of 1 to mean either a constant or a constant function with respect to some variable. The real problem is that our ordinary notation for functions does not distinguish functions from values. In lambda calculus, the parameters to a function are clearly specified. The function n square could be written as lambda n into n square or even lambda r into r square. Adopting a more rigorous notation, however, would complicate algebraic manipulations, so we chose to tolerate abuse. The O notation, the theta notation, asymptotically bounds a function from above and below. When we have only an asymptotic upper bound, we use O notation for a given function g of n. We denote by O of g of n, pronounced as big O. Okay, I was pronouncing it wrong the whole time. It is not just O, it is a big O. Right? So big O of g of n or sometimes O of g of n. Okay. The set of functions of g of n equal to f of n such that there exists positive constants c and not such that they just remove the lower bound. And this zero is important for the non-negative asymptotic functions. We use big O notation to give an upper bound on a function to within a constant factor. Figure 3.1b shows the intuition behind big O notation. We saw it earlier where we have an upper bound c into g of n. For all values n at and to the right of n naught, the value of function f of n is on or below c of g of n. When we write f of n equal to big O of g of n to indicate that a function f of n is a member of the set. Note that f of n equal to theta of g of n implies f of n equal to g of n. Since theta notation is a stronger notion than big O notation written set theoretically, we have theta of g of n a subset of big O of g of n. Thus our proof why it is a subset of big O notation is that for big O notation the lower bound we are not setting, so it is a much larger set than theta notation. Thus our proof that any quadratic function of an square plus bn plus c where a is greater than 0 is in theta n square also shows that any such quadratic function is in big O notation. What may be more surprising is that when a is greater than 0, any linear function a n plus b is in big O of n square, which is easily verified by taking a c equal to a plus p, ignoring the sign, and n not equal to maximum of 1 comma minus b by a. If you have seen O notation before, you might find it strange that we should write, for example, n equal to O n square. In the literature, we sometimes find big O notation informally describing asymptotically tight bonds, that is what we have defined using theta notation in this book. However, when we write the function, we are merely claiming that some constant multiple of g of n is an asymptotic upper bound on f of n, with no claim on about how tight an upper bound it is. Distinguishing asymptotic upper bounds from asymptotically tight bounds is standard in the algorithms literature. So big O notation we can often Using big O notation, we can often describe the running time of an algorithm merely by inspecting the algorithm's overall structure. For example, the doubly nested loop structure of the insertion sort algorithm from chapter 2 immediately yields an big O of n square upper bound on the worst case running time. The cost of each iteration of the inner loop bound is bounded from above by a big O of one constant, and the indices I and j are both at most n, and the inner loop is executed at most once for each of the n square pairs of values for I and j. Since big O notation describes an upper bound, when we use it to bound the worst case running time of an algorithm, we have a bound on the running time of the algorithm on every input. The blanket statement, as we discussed earlier, thus the big O notation of n square bound on worst case running time of insertion sort also applies to its running time on every input. The theta n square bound on worst case running time of insertion sort, however, does not imply a theta n square bound on running time of insertion sort on every input. For example, we saw in chapter 2 that when the input is already sorted, insertion sort runs in theta n time. Technically, it is an abuse to say that the running time of insertion sort is a big O n square, since for given in n, the actual running time varies depending on the particular input of size n. When we say the running time is big O of n square, we mean that there is a function f of n that is such that for any value of n, no matter what particular input of size n is chosen, the running time on that input is bounded from above by the value of f of n. Equivalently, we mean that the worst case running time is big O of n square omega, just as big O notation provides an asymptotic upper bound on a function. Omega notation provides an asymptotic lower bound for a given function g of n. We denote omega of g of n pronounced as big omega of g of n, or sometimes as omega of g, the set of functions such that for all, okay, they have interchanged the limits. This is theorem 3.1. For any two functions f of n and g of n, we have f of n equal to belongs to theta of g of n if and only if f of n equal to omega of n, and so it contains an upper bound with relation to g of n and a lower bound with relation to g of n. Then it belongs to theta of g of n, but that n naught should be the same for both O and theta, and C1 C2 is depending on if big O and big omega, and yeah, anyway, greater than 0 is in both. As an example of the application of this theorem, prove that a n square plus b n plus c equal to theta of n square for any constant, where immediately implies that omega n square, and in practice, rather than using theorem 3.1 to obtain asymptotic upper and lower bounds from asymptotically tight bounds, as we did for this example, we usually use it to prove asymptotically tight bounds. When we say that the running time of an algorithm We mean that no matter what particular input of size n is chosen for each value of n, the running time on that input is at least a constant times d of n for sufficiently large, and equivalently we are giving a lower bound on the best case running time of an algorithm. For example, best case running time of insertion sort is omega of n, which implies that the running time of insertion sort is the running time of insertion sort therefore belongs to both omega of n and pico of n square, since it falls anywhere between a linear function of n and a quadratic function of n. Moreover, these bounds are asymptotically as tight as possible. For instance, the running time of insertion sort is not omega n square, since there exists an input for which insertion sorts run in theta of n time when input is already sorted. It is not contradictory, however, to say that the worst case running time of insertion sort is omega n square, since there exists an input that causes algorithm to take omega n square time. Asymptotic notations in equations and inequalities. We have already seen how asymptotic notation can be used within mathematical formulas. For example, in introducing O notation, I will cover this later.